Lecture 32, Probability, Convergence, Ergodicity. So as a quick preface, to understand some of this material, you would be well served to have at least some familiarity with the subject of probability and what have you in your past, in your background. You may have taken a course on probability earlier. It's possible that that material is not very fresh in your mind. There's a couple of things linked in the notes that you could review if you wanted, but we're going to go over some of it in brief. If your probability course was anything like the one that I took, it was really taught from a perspective of math and just pure math, and these are the formulae, and these are the numbers, and this is how it works, with relatively few connections to anything, say, computer software. So I'll try to link certain things to a use case that might appeal to you in the hopes that it will aid in your understanding, help it stick in your mind a bit better than would otherwise happen if it all just seems kind of abstract and the numbers do this and go here and do that. Just let's hope it works. Okay. Yeah, suppose we want to do an experiment like rolling some dice. Want to play some D&D? Got lots of different dice in D&D, and you can have lots of different outcomes. And if you don't watch Critical Role, it might be up your alley, it might not. But maybe don't start during an academic term. It might take more of your time than you intend. Okay. We associate an outcome of doing an experiment in this case being a roll of the dice, with something called a random variable. A random variable, capital X, has many instances, each with some probability. So if it's a six-sided die and it is perfectly fair, then this die can have instances of 1, 2, 3, 4, 5, and 6. And because I said it's perfectly fair, and it is by definition the case, then each of those things has a probability of 1 out of 6 of occurring. In a die roll, we would say this is discrete because there are only the fixed values 1, 2, 3, 4, 5, and 6. You can't roll 2.1 or 5.5, and so for that reason, we say it's discrete as opposed to continuous. Usually when we talk about computing, we measure time as continuous. We treat it as being, you can break it down into arbitrary segments. Whether or not that holds up for your particular use case depends a lot on the time frame in which you are working. If we are looking at wall clock time measured in seconds, then sure, you can subdivide to your heart's content and you can treat it as continuous. However, if you are looking at something that happens in very, very short time frames, then you get into the problem of the resolution of time of the computer, which is to say that there are limits to how accurately you can measure time using the computer. And if you are dealing in that realm, then you might actually end up treating time as being discrete because discrete time steps occur on a scale where it matters for you. So, all right. Yeah, the resolution that you face is very dependent on your hardware. So I roll the dice, and whether it goes well or badly, we have an outcome, and we consider the outcome of an experiment to be an event. And so each time I roll the dice, that's an outcome, and that is an event. So, all right, given the information that we have, we can start to ask questions like, what is the probability of rolling 4 ones on a 20-sided die in a row? Assuming your die is perfectly fair, which is not necessarily the case because they're not always manufactured, at a level of perfection. Sometimes they have various imperfections in them. But if it's perfectly fair, then there's a 5% chance on each roll that it turns up a 1. And you can say to yourself, well, what is the chance that, we roll this 1 5 times? It's, well, You may believe things like, my character is unlucky and therefore it's going to happen frequently, or you may believe my character is lucky and this will never happen to me. You don't know really in the end until it actually happens whether it's going to happen to you or not, but you can estimate what the probability of it is simply by doing the math. If you wanted a different analogy, one that involves fewer Dungeons and Dragons, you could also imagine from the perspective of application programmers, if you say the number of users at time t is represented by a random variable u, you can ask, what is the probability of u being greater than 1,000? What is the chance that 1,000 users or more than 1,000 users are using your application right now? Sometimes it's not your day. You're lost in a forest with no roads? Locate a native, ask for assistance. Careful what you wish. You just might get it. Okay, so given some model for user behavior, we could put together some calculation that tells us the probability of saying that more than 1,000 users are using the application right now. We don't necessarily have a model of the user that we can work with out of the box because every user is going to interact with the application differently. And it's not as simple as rolling dice. When we roll dice, we can say, yeah, for sure, the behavior of a die is known. We can say, yeah, this is how it works, and our expectation is that it stays that way. Users, of course, are a lot more fickle. They behave in ways that make sense to them, but not necessarily sense to you. And they can change their behavior. They moved to a different city that's in a different time zone, so they use the app at a different time of day now, right? That kind of thing you would presumably want to account for in your user model, at least to some degree. Now, the probability is usually defined as some sort of experiment with a sample space omega, and some subset E of omega is an event, in full generality. Just, so StatsProf doesn't beat me up and, leave a bad review. Sample spaces are measure spaces. So in a standard example, you have a perfectly fair coin. Usually we say, well, it's 50-50. So 50% chance that it happens to be heads and 50% chance it happens to be tails. If you want to be pedantic, you could say it could land on the edge, which is not impossible. So we might consider that to be a plausible outcome, even though it's really unlikely. Okay. And we would say that each outcome is an event with a certain probability, so we would say P, and then in curly braces, E of n, E being the event and n being the assigned number. So we would say probability of heads is 50% and probability of tails is 50%, again, assuming that our coin is perfectly fair. Which, when we are defining the coin, as a hypothetical, then yeah, that's easy to achieve. An actual coin in real life may not be manufactured to such a standard, depending on what designs are on each side of it, if nothing else. Okay. One of the things I want to make a point of talking about is not confusing the idea of independence and mutually exclusive. If I feel independent, it means I'm not constrained by others, but things are a little different when we talk about probability here. If the coin comes up heads is going to be defined as event E1, and coming up tails is event E2. We ask, are these independent? And the answer is no. They are actually mutually exclusive instead. Mutually exclusive means that if one happens, the other can't happen. So if the coin has landed with the head side facing up, it can't possibly also at the same time have landed with the tail side facing up. So that's important to make a distinction about. Independence would mean something like if I flip coin 1 and it comes up heads, and then I want to flip coin 2, will the outcome of coin 2 be affected by what happens with the first coin? No, it isn't. So we would say those are independent. So that highlights a little bit the difference. Events are sets, and you can do things like unions and intersection and stuff like that. So you could say actually the formal definition of mutual exclusivity is E1 intersect E2 is the empty set. Independence, on the other hand, means the probability of event 2 does not change if event 1 has occurred, or event 1 does not change if event E2 has occurred. That's also fine. Another formula that you will probably need in some circumstances is the conditional probability formula, and it is given that event F has occurred, what is the probability that event E will occur? And the notation is probability of E given F, and has a notation as long as probability of F is not 0. Of probability of E given F is the probability of the intersection, so both E and F, divided by the probability of F. Okay. To think about a conditional probability kind of thing, if you know that the temperature is above 10 degrees, what is the probability that the temperature is also above 20 degrees? If we know that F has already happened, it's above 10 degrees, there is some possibility that it's above 20 degrees, but maybe it's not. Maybe it's only 15 degrees, maybe it's 25, we don't know. And you can represent that kind of thing with a conditional probability. We have some information, and it tells us, all right, it's at least 10, but is it going to be more than 10? Don't know yet. We'll find out. Okay, if events E and F are independent, which they're not in the case of temperature, then probability of E intersection F is the same as just the multiplication of the two, because the probability is not affected by the occurrence of it. And so suppose you flip a coin 4 times and it comes up heads each time. We'll call that event F. What's the probability that the next coin flip will be tails? We'll call that event E. Well, sadly, a lot of people think that after 4 heads, tails is now due, and the chance of it being tails is higher than the usual 50-50, minus whatever edge case. This is not true. The next coin flip is independent of all the coin flips that went before it. Where things get kind of off the rails is that if we're at the start of coin flipping, I flip no coins, I've got a coin in my hand, and all right, I'm going to flip it, and we discuss what is the chance that I'm going to get 5 times heads in a row. Pretty small, right? We'll calculate it. No problem. It's 0.5 to the power of 5. It's a small number. Fine. However, if at this point I have already flipped it 4 times and it's come up heads every single time, the past is the past, and the coin doesn't have a memory in the sense that it doesn't remember that it's been heads a lot and it needs to somehow be tails now. And given that these things have already happened, the next coin flip is still already 50-50. So even though it's unlikely from the outset that I would end up with getting heads 5 times in a row, when it's already happened 4 times, the hard part is, I won't say over, but mostly over, and therefore it's more likely that the next coin flip is just going to be 50-50 because everything is the way that it is. Doesn't change. With that in mind, if your coin is consistently coming up heads way more than you might expect, and you're doing a real experiment with a dollar coin or something, a loonie, you may start to think at some point that the coin is maybe not fair, which is also perhaps a reasonable conclusion, although I wouldn't jump to that if it happened to be heads 5 times in a row. That's possible, but unlikely. Of course, everything is possible, if unlikely. Okay. A statistics prof would also be upset with me if I didn't tell you about Bayes' law. And if you want probability of F given E, but we have probability of E given F, can we get the reverse? Sure we can. Very simple. As long as we know what the probability of F and the probability of E are on their own. And the probability of F given E is the probability of E given F times probability of F divided by probability of E. So, straightforward math formula that allows you to shift things around in case you are presented with this information and you need that information. Here's how we do it. Nothing hard there. Okay. basics over onto trying to apply a couple of things. We're going to talk for now about discrete random variables. That is, they have a countable number of values. You can't have 2.5. They're only integer values. For example, that would be a discrete random variable. And for a random variable x, we can define a probability mass function of p sub x of a is the probability of x equals a, where the sum of all of those probabilities equals 1. So what we're saying is the probability mass function of an outcome a is equal to the chance that the random variable happens to be that value. So if it's a die that we're rolling and it is perfectly fair, the probability that we roll a 6 is exactly the probability that we rolled a 6. We already know it's 1/6 because we said that it's perfectly fair, and so the probability mass of the outcome of rolling a 6 is 1/6. And all of them have to add up to 1 because only the possible outcomes need to be considered, and so we can say, yep, this is true. The cumulative distribution function is the f sub x of a, which is the probability that x is less than or equal to a, which is the sum of those individual chances. So you're playing a game and you need to roll at least a 4 on your 6-sided die. So you can calculate the cumulative distribution function by saying, all right, what is the probability that x is less than or equal to a? And it'll tell you, all right, so we have to consider the chance that it's equal to 1, you have to consider the chance that it's equal to 2, and the chance that it's equal to 3. 4 or above is sufficient. And, all right, that gives you your cumulative distribution, so that's half. And because we calculated, we said we wanted 4 or above, we have to do 1 minus that value, but 1 minus half is just half, so nothing super exciting happens there. But we can use this cumulative distribution. For a die where we've said every outcome is equally likely, these kinds of things are maybe very simple. They maybe sound a little bit trivial, but you can, of course, imagine that in a real scenario, the probabilities for different things are different, and it's not always just, 3 possible outcomes, each of which is equally likely, or 6 possible outcomes, each of which is equally likely. That's fine. We use dice here because it is convenient to think about, not necessarily because it is a good analogy for everything in real life. Okay, there are 5 distributions. There are 4 lights, but 5 distributions that we want to discuss: Bernoulli, binomial, geometric, Poisson, and exponential. All right, we'll talk about each of them in a little bit of detail. And some of these matter to us a bit more than others. So we'll start with Bernoulli. And the Bernoulli distribution is kind of like a coin flip. It says a coin has a probability p of coming up heads and 1 minus p of coming up tails. So a random variable x that is associated with it evaluates to 1, let's say heads, with probability p, and 0, tails, with probability 1 minus p. And that's how we would represent something that wasn't necessarily a fair coin. Maybe it's an unfair coin where it has a 60% chance of coming up heads, and that would be a way of saying, yep, we will say that if it's 60% chance of coming up heads, then the p is equal to 0.6, and tails is 1 minus 0.6 equals 0.4. So the probability mass function is equal to p, and so it's easy. The binomial distribution builds on that. It says, all right, a coin with probability p of coming up heads is flipped n times, and we have to assume that these are independent, but that's okay. Again, if we're flipping a coin, I don't think we mind. And that is, so random variable x represents the number of heads when flipping a coin x times. So x takes on values anywhere from 0 to n. In the scenario where it never lands on heads, then that's 0. In the scenario where it always lands on heads, it's n. And somewhere in between, it lands heads some number of times, sometimes not always. Okay. So that gives us an idea of how many coin flips will end up with this outcome, or so heads. The geometric distribution builds on the Bernoulli distribution, and suppose that we have a coin with probability p of coming up heads. I want to know how many times will I have to flip the coin until it lands on heads. On average, of course. X represents the number of flips until we get the result we want. It could be the first time, it could be the third time, it could be the 10th time. You don't know really until you actually execute the experiment, but you can say on average we think it will take about this many times before you get heads. Okay, so let's try to relate those to computing. Suppose we have a server farm, and the server farm has n hard drives in it. You can imagine them as SSDs or anything like that if you wish. But imagine that we have those, and each of which has independently a chance of dying or failing with probability p in a given year. For the record, by the way, if you actually want to have this behavior where drives are independent, you shouldn't be buying more hard drives from the same box, from the same manufacturing lot, because they tend to live about equal lives, and so if you are trying to build a backup device or network attached storage or something where you're trying to back up your data, there's a chance that you suffer multiple drive failures in a short period of time because they were all manufactured all at the same time in the same batch. So you got to be a little bit careful with that. But let's assume that we don't have that problem and that every drive here is completely independent, and that's okay. Right. So we've discussed three models, and now I want you to match the model with each of these questions. Number one, how many disks die in the first year? So at the end of the year, if we didn't do anything, we just look at the drives in the server room. How many of them have died? Question two. Given a particular disk D, go to a server, point at it, look at the drive inside. How many years until it dies? And question three, at the end of the year, given a specific disk, is it alive or dead? Again, pick a server, point at it. At the end of the year, what is the chance it is alive? What is the chance it is dead? All right. So hopefully, looking over the previous slides, you've got an idea of what the correct answer is. But the answers are 1, binomial, 2, geometric, and 3, Bernoulli. Why does this make sense? Well, how many disks die in the first year? This is binomial. You flip some number of coins, so each drive is flipping a coin. If that coin comes up heads, the drive is dead. And at the end of the year, you have some number of those that ended up in that situation. Some do, some don't, and you have anywhere between 0 and n drives have died. Okay. Number 2, geometric. Given a disk D, how long until this disk dies? So every disk, every year is flipping the coin, and if it comes up heads, or if in D&D speak you roll a 1 on that, time to die. And so how many times do you have to flip the coin before a particular disk dies? We'll find out with geometric distribution. And then Bernoulli for the last one, which is given a disk in particular, roll the dice on it. If you get a bad outcome, it dies. All right, either it happens or it doesn't. That's how we relate those distributions to a computing context. All right. I also want to talk about the Poisson distribution, which is very common in computing. This represents our natural idea of randomness, and this distribution arises when we have a very large number of sources, each with a small probability. So the chance that I, right now go to twitter.com is not very high. There's a lot of time in the day, and I don't spend all of it on Twitter. And so there's a small probability that I decide to look at Twitter right now, right this very moment. However, there's a very large number of users of Twitter, so at any given time, probably at least some people are looking at Twitter, all over the world, and making the website popular, giving it usage. And so arrivals to a website or packets to a router in some particular unit time is a good candidate for modeling it with a Poisson distribution. If a random variable x has a Poisson distribution, then the probability mass function is e to the negative lambda times lambda to the power of I over I factorial, where I is 0, 1, 2, and so on and so on, which gives you some breakdown of like how likely it is that we're going to have at least at least this many events at a given time. We'll also talk about the exponential distribution, and the exponential distribution is one where the probability mass function drops off, well, exponentially. So if x is greater than or equal to 0, then f(x) of x is lambda times e to the negative lambda x. So again, fancy math stuff. Just says that the cumulative distribution function decreases exponentially, which is sometimes nice. You might want to observe this behavior, or you might see this behavior if you are talking about job size. If job size is exponentially distributed, it means most jobs are small, and as time goes on, the jobs that you get are likely to be small, but there is a progressively lower and lower chance of getting a job that is larger and larger. And that's usually what we care about is the inverse of this, capital F of x with a bar on it, of x. The probability the job is greater than that. So you might be interested in something like, what is the chance that it takes more than 5 minutes to execute this query? Right? Those are the outliers. Those are the tail of the distribution. And if you have an exponential distribution, then you see a drop-off of e to the negative lambda with each unit increase of x. And so it prevents a sad situation where you have a very heavy tail. That is to say, you have a lot of outliers, things that are above this threshold. Okay, we'll close out with a couple of other things just in terms of notation and rounding out our probability discussion. The first one, the notation E and then square brackets around x, is the expected value of a random variable x. And this is to say that it is just a weighted average. When I took my probability course, this wasn't explained to me real well, so I had some difficulty sort of grasping this until somebody said that to me, and I was like, oh wait, that makes a ton of sense, and now I finally understand a lot better what we're talking about in this topic. So if you're entering into a game, let's talk about gambling. Not that I recommend you gamble, but if there is a gambling game that you are looking at, it is, in this scenario, you have a 50% chance of you get nothing, a 10% chance you win $10, and a 40% chance of getting your $3 back. Should you play? I mean, it's easy to do the math because you can calculate the expected value, and your expected return is for every $3 that you put in. There's a 50% chance it's 0, so 0.5 times 0. A 10% chance of getting $10, so 0.1 times 10, and a 40% chance of just getting your money back, so 0.4 times 3, which is 0 plus 1 plus 1.2, resulting in a total of 2.2. That is that for every time you play this game, on average, you expect to get back $2.20. That doesn't make it a good investment, does it? I mean, I don't think so. Econ 101 logic, however, will tell you that really part of what matters is did you enjoy playing? Did you feel hope and excitement of winning? Did you have a good time playing this game? If you did, then maybe it's worth it to you. Fun that doesn't turn a profit is still fun. If I go in a non-pandemic time and see a movie in the theaters, I'm not expecting this is going to be a profitable activity. I'm going to pay money. I'm going to see the movie. I will enjoy it, hopefully, but it's not going to turn a profit. And in principle, a gambling game could be the same thing. That you could enjoy it even if you lose money because you enjoy the activity. Please don't take this as some sort of endorsement of gambling, but you could enjoy it, and there wouldn't be really anything wrong with that. All right, I'm going to give you a couple more things as proof of because I said so. Just take my word for it that the expectation for a geometric distribution with probability p is 1 over p, and if a Poisson distribution applies, the expected value of lambda is lambda. These matter for things like arrival rate, and we'll just refer back to these values when we need them. The weighted average is nice, but it's not the whole story. If your numbers are 5, 6, and 7, then their average is 6, but the average of the numbers 0, 6, and 12 is also 6. And in some cases, the variance is important to users. Things that take a known amount of time is understood and acceptable, but things that sometimes are done very fast and sometimes take a lot longer can actually be very frustrating for users, because in the scenario where it takes longer, they think something is wrong, it's gotten stuck somehow, there's a problem, and we need to restart or something, which isn't always correct. Sometimes a little patience is really all that's necessary. So we should already know that averages can be a little bit misleading. If you have an average arrival rate of 1 request per second, with some probability, there is a chance that you get 3 arrivals in a single second. So don't be misled into thinking that if an arrival rate is an average, there's no variance in it, and it means you always every 1 second regularly get an arrival. That's not necessarily true. The variance in this matters a lot, and you need to be able to handle that variance, just by having a queue where you keep things where data is going to be stored until you're ready to process it. Okay, and the formal definition of variance of a random variable x is the expected squared difference of x from its mean, which is the expected value of x squared minus the squared version of the expected value. And again, I don't believe there are too many scenarios where you need to know how to calculate this, but this is some information that I want you to have at hand when we look at thinking about arrival times and stuff like that. And again, I want you to just take my word for it on the for the moment that the expected values and means and variance things here are correct. A Bernoulli distribution has a mean of p and a variance of p times 1 minus p. Binomial is np with a variance of np times 1 minus p. And so on and so on. For geometric, 1 over p. For mean, variance 1 minus p over p squared. And Poisson, you get lambda in both situations. And yeah, these are some distributions, facts and figures that you might need at hand for actually assessing what is the probability that something is going to happen or not happen in your program, and we can hopefully put some of these things to use in the upcoming topic. There's a lot more that you should know about conditional probability, exponential distributions, that kind of thing, but I just want to be sure that everybody has a base understanding of probability before we go on to talking about some of the upcoming things.